Today I want to talk about managed aquifer recharge concepts, and it's a pretty high level just summary of concepts. It's based on a paper I was fortunate enough to do for Applied Geology, fourth edition that's coming out here. And so I got to dive into the regulatory framework, some of the historical aspects of managed aquifer recharge, and also ASR. Right off the bat, because I am no expert on this topic, I am basically, I know enough to be dangerous, and I love to do this type of work, and I'm always pursuing to do more. So Mr. David Pyne, I bought his book at the Bismarck conference back in 2014, and had a great talk with him. He really has inspired me. Hank Baskey, you'll see some of his products in this talk. He's a pioneer when it comes to flow control valves. A fellow Australian, Peter Dillon. I was fortunate enough to meet him and when I was in Adelaide, and I got to visit the Salisbury constructed wetlands project there, which I think is phenomenal. If you ever get a chance, you got to see it. And then a couple local talent here. Chris Peterson is one of our Northern California kind of MAR experts, and is involved in a lot of projects, and is kind of the forerunner in this region. And somebody in the audience, Mr. Tim Parker, he wrote some papers for previous Bismarck, and I found him in the proceedings and asked his permission to use some of his work. He's an expert with as far as regulatory and some of the directions the new legislation is going. And we are trying to streamline the process for managed aquifer recharge projects. So you've seen a couple definitions already. You look for a suitable aquifer. You try to get water in there via a well or a surface feature, and you try to recover the water when you need it, hopefully in a dry year, and you get the water in during a wet year. That's pretty much it in a nutshell. Here's a kind of conceptual model. I tried to tailor this for agricultural water topics, and so as you'll see, a lot of this springs from necessity, and a lot of the water districts or a lot of the operational water banks came out of overdraft conditions due to too much pumping, or problems with they pump so much they got seawater intrusion, or we have land subsidence. Some of the big issues in the Central Valley. I think we've all seen the picture of the USGS scientists standing next to a telephone pole, and there's a sign, an area where it used to be land surface, and 28 feet below is where he's standing now. So we have some big problems. As Lester Snow says, I think I got his name right, that we have a lot of storage space waiting for groundwater to be put into it. We've done scientists a favor there with some of our practices. Wet season, and then it comes out in the dry season. As you can see on this, you see some irrigated lands there, wetland basins, treated water, all different types of sources that are becoming more and more available for recharge. Here's some selected sites that I put into my paper. We have Orange County, Water Replenishment District. We have that spot over there by Bakersfield I'm going to talk about is a Kern water bank. And then we have Santa Clara Valley Water District. Orange County and Santa Clara Water District, they've been doing this for over 60 years. So there's a lot of good industry experience there, a lot of expertise. And I think California has a lot of potential to get this into maybe the more of the agricultural community. The reason I brought this topic is that there's so many. Where are the wells at? Where are the straws to get water into the ground? It's usually on these agricultural irrigated lands. They have all the wells. They already have a lot of the infrastructure. They have a lot of the power supplies there, a lot of the roads. So maybe they're going to be a player in the future. Just as an example of an area, Orange County, water district formed in 1933 by a special act of California legislature. Probably would not happen as quickly as it happened then in today's regulatory and legal environment. I think that needs to change. But it sprang out of necessity, overdrafts, seawater intrusion, lots of people fighting over water, falling water levels. So now they have a system in place that gets about 280, 300,000 feet of recharge per year, and a lot of that comes out. They have a base pumping percentage that they set, so they have freeboard. They work within a range, you know, so they don't want to get it too full and they don't want to get it too empty. Thank you. We went on a tour there. This is like just one of their spreading grounds canals, you know, with the weir system, and this is just one of their many channels and canals that they get the water into. They do this year in and year out. It's amazing what they do there. The Kern County Water Bank, it's up there in oil and gas country and farming country, north of Bakersfield. It's also hydrogeologically suited for recharge because there's thousands and thousands of feet of sediments that are conducive to recharge in this area. And it's just really blessed by its location to the aqueduct, the Kern River, the Friant-Kern Canal, and all these appurtenances that can get water to it. And so they got together. There's a complex agreement to kind of fallow a lot of this land or take it out of agricultural hands with the promise of using it as a water source. The Department of Water Resources, the state water project contractors got together. They hammered out something I think was called the Monterey Agreement, and they formed this complex water bank. And they've gotten about, they said they've recovered about 0.9 million acre feet. That's as of 2011, probably a lot more now. So what they do is a very complex system of water wheeling, water trading, negotiations to get the water in the ground and to get it into the aqueduct during dry years. It's very complex. It's like it's a water bank, you know. It's like a big time, you know, moving money around. They're moving water around. It's pretty fascinating. And this is kind of a conceptual picture of what they do there. You can see the Kern Canal, the Kern River, the aqueduct, and that's kind of what they do. They get it in the ground, and then they have recovery wells, and they have hundreds of recovery wells that get the water into canals and the aqueduct for buyers downstream. And what this was 20,000 acres of irrigated land, farmland, that has now been used for a water bank. So kind of goes into the potential, you know, the potential for California to get out of our large critical overdraft situation, I think exists with a union between private entities, public entities. When I say private entities too, I'm talking about private pumpers, private landowners. Now to get into some of the more of the planning aspects of this, site selection. The UC Davis Ag Extension, along with some consultants they hired and some, maybe I believe some other, the Water Education Foundation and maybe Water in the West, some kind of nonprofits, got together and came up with the Soil Agricultural Groundwater Banking Index. It's online now. It's a web application that you could use as your first point of contact or research, and they look for suitable surface recharge areas, and you can almost use it too for groundwater recharge research too if you want to find some groundwater recharge sites. And they're looking, the following factors they look at is deep percolation. You know, obviously, if you want to get water down into the aquifer, it has to have that good vertical connection. The root zone residence time, you've been hearing that a lot in the news right now. What plants or perennial crops can take long-term surface water flooding or diversions? You know, I think they're saying grapes are pretty good, almond trees are pretty good, maybe walnut trees or something else not so good. They don't like having their roots soaked that long. So that's something to take into consideration. Central Valley salts are always a problem. You have to worry about your water chemistry, your water mixing models, topographic limitations. If you're going to use surface water and impound it or divert it, make sure it stays where you want it to. Surface conditions. This kind of gets into the soil chemistry and the mixing models. You want to know what your sodium absorption ratios are, the erosion factors, you know, and just how is this going to hold up to long-term flooding, drying cycles, flooding, cleaning out, and then flooding again. So Orange County Water District, Santa Clara Valley Water District are really good models there. They have a lot of good online information or documentation. More site selection stuff. You know, obviously, if you're going to get into the planning, you know, plan to succeed. Don't plan to fail or fail to plan. Something, you know, you've heard those. So just make sure if you're going to use, like I've worked with some ag clients, and right now some projects, it just brings up all these regulatory red flags. Unfortunately, private pumpers or private landowners seem to run afoul more of the regulations than public agencies, and it's too bad because a lot of these people do want to do sustainable type of projects. Obviously, you want to get out there, start doing your field studies. A big one is know where your faults are, know where the groundwater is going to flow to. There's a couple I could do a whole slide on a couple of case scenarios where there's success and there's abject failure because they didn't map faults and groundwater went where it wasn't supposed to go, and the recovery wells were, you know, sucking air, so to say. You don't want that to happen. Test well drilling. This is for your ASR and basin studies. You want to I could do a whole session on the technical aspects of ASR well design, and I won't bore you with that, but there's a lot to it. I'm really skimming over a lot of this, but ASR wells, recovery wells, are different than just pure pumping and extraction wells. Here's an example of a I'm going to get into some of the technology, but here's managed aquifer recharge well with flow control valves, and that gets into MAR technology. And basically, to control your downhole flow, you're going to either use packers, flow control valves, or more advanced aquifer storage and recovery valves. Oxygen, turbulence, all that are the enemies. You want to have that smooth flow. You want to keep the oxygen out. You want it to be, you don't want to create a vacuum. You want to get that water in the ground, and you don't want it to be disturbed, so you have geochemical changes taking place. So here's some packers. Full flow, the packer's closed. No flow, the packer blows up. Talking about the baskies, here's a big flow control valve you can put in line in a usually a turbine pump system. Here's a worksheet. Don't worry, there won't be a test. That's just to kind of show you some of the planning references or tools available out there that go into this for a successful program. Got to give a shout out to the Aussies once again. Here's AG Development. They have an ASR valve. They're out of Western Australia, and this is pretty much state of the art for flow control, downhole, and it rotates and allows the water to be extracted. Here's kind of an example for startup calculations. You know, this is the type of worksheet that's developed. His name didn't get in there, but I think this is from Tony Scott. He runs the Los Angeles ASR well field, one of the biggest ones in the United States. He was trained under David Pyne, excellent source of knowledge and experience. So what I geared this to in summary, as the Sustainable Groundwater Management Act takes effect, I believe MAR projects will be to include groundwater replenishment projects, indirect potable recharge, aquifer storage and recovery. I think these methods will become more frequent. I think these type of projects, we're going to need more professionals. It's multidiscipline, you know, engineers, chemists, earth scientists, process engineers, mechanical engineers, hydrogeologists, groundwater modelers, geochemical modeling. It all goes into a successful program. So get a good team right off the bat, do a really good feasibility program, a lot of pilot testing, bench testing, keys to success. And so I hope this provides you a reference and a resource to understand these concepts in groundwater management. And thank you. Are there any questions? Popular.
Yeah, just one comment on something you said, which I think is important about you should know where your water is going from and to and plan for that. And I think that basically is very true for MAR projects, but incredibly true for all sorts of other hydrogeologic projects, which I think people really miss the importance of, whether it be for a production well, modeling, that you really need to have a good conceptual model. And I think that's not enough time is spent on that, and that you really, with a good conceptual model, that's an incredible building block for the rest of the project. So I compliment you on pointing that out.
Thank you. I totally agree. And one of the resources we have for conceptual models are those wells that are drilled out there by the private pumpers who have the majority of the wells. And if you could get other well logs, but that's what I think Sigma in general is going to be built on good hydrogeologic conceptual models.
Any other questions?
Yes, my experience with recharge, I'm familiar with the Orange County one and the one in Kern, alluvial fan. You mentioned a well field somewhere in the Los Angeles area, I understood.
Las Vegas.
Okay, have you seen any successful large-scale injection using wells? Because it's not an easy operation to recharge a lot of water with wells hydrogeologically. So have you seen any successful operations in that respect?
Mostly, like you say, it's small scale, and then the large scale Las Vegas, I believe they get in 500,000 to 1 million acre feet, maybe less than 500,000 acre feet, and it's a large amount of infrastructure and a large amount of operation and maintenance. It's probably the more difficult way to do it, but it's born out of necessity. You know, Las Vegas has the money, but it has the critical need, and the basin is pretty compatible. The water stays there, it can be extracted easily. But if you're looking at like in the Central Valley, I believe you're going to have some more people working together, because the water is going to be flowing away from a lot of the recharge sites, so it'll take a lot of coordination and stuff. But I mean, you know, it's probably the worst case scenario is what California groundwater basins are in right now, and you know, how are we going to reverse those trends?
Is it really always a problem if the water you injected moves away from the well? It's not necessarily a problem if it is replaced by a similar water quality, and you still keep the basin up to its level. So, yeah, maybe not a question but a remark. It's not necessarily a problem.
Right, I agree. It was started out in confined aquifers, and they used freshwater and brackish water, and now it's you know, kind of morphing into more just getting water in the ground and recharging aquifers. Absolutely.